Welcome everybody. This is going to be a short video about minerals. So we're going to give a basic overview about what minerals are, how do we identify minerals with their common properties, where to find some of that information in the Earth Science Reference Table. So the very first thing we need to know what minerals are. In order to do that, we need to understand the kind of 5 properties that minerals must have in order to be considered a mineral. Okay, first off, they need to be naturally occurring. That means if you have something that was made in a lab, it's not a mineral. It's man-made, synthetics are by definition not minerals. They need to be inorganic. They need to be solids. They need to have some sort of internal or atomic structure. So basically they have some sort of crystalline structure to them. And lastly, they need to have a chemical composition that falls within a defined range. All right, so for example, the mineral quartz is always SiO2. The mineral olivine has a little bit more of a range to it. Could be iron or magnesium 2, and then SiO4. All right, so there is some leeway in the chemical composition, but it's within a very narrowed range. Okay, so this term inorganic, if you're wondering what that means, it means that minerals cannot form from living organisms. And then of course, they need to be a solid, so you can't have any liquid or gaseous materials being considered minerals. All right, so if we take a look at the naturally occurring solid of ice, ice is naturally occurring. You can find ice out in nature. It's inorganic, doesn't come from any living things. It's solid. It does have an internal or atomic structure that's ordered, and it also has a chemical composition within a defined range. So ice is a mineral, but the liquid phase, water, is not, because water is, of course, not a solid. It's a liquid. Okay, so the next thing we want to take a look at are mineral properties, and you're going to find those mineral properties on the Properties of Common Minerals page on the back cover, page 16 of your Earth Science Reference Table. So we'll get into this in just a minute. But first, we want to take a look at what the properties are. We have luster, hardness, breakage, which is subdivided into cleavage or fracture, color. Notice the red flag here. You need to be a bit wary of using color for identification purposes. And last but not least, we have streak. So instead of using color, streak would be a better property to use. All right, so you might be asking yourself, well, where do we find these things? Luster is the very first column, the leftmost column of the Earth Science Reference Table. Hardness is right next to it. The type of breakage, either cleavage or fracture, is listed in the next column. The check mark means that that particular mineral demonstrates cleavage or fracture. Fourth column over is where you're going to find your common colors. Again, be a little bit wary of using color for identification purposes. Talk about that in a few minutes. And last but not least, streak you can find in distinguishing characteristics. Right, so the example here, pyrite has a green-black streak, which is very, very useful because the mineral itself is a brassy yellow color. Looks a bit like gold, but its streak is green or black, or green to black. Right, you might be wondering, now why do all of these minerals have different properties? And it all comes down to their internal or atomic structure. The regents will use both terms, internal structure and atomic structure, interchangeably. So this is what controls all of the physical properties of any given mineral. And a classic example here is the structure of diamond, as you can see on the right-hand side, versus graphite. Chemically speaking, both diamond and graphite are identical. They're both just pure carbon. But their structures, as you can see in the images, are completely different. Diamond has very strong bonds between all of the carbon atoms, whereas graphite has weak bonds in between these different layers or sheets. Right, so that's why diamond is very, very hard. It's a 10 on what's known as the Mohs hardness scale. It's the hardest naturally occurring mineral that we've discovered. And then graphite is a 1 to 2, very low, very soft mineral on the hardness scale. This is actually what you use to write with if you're using a pencil. Okay, so we're going to go through each one of these properties now. So luster is simply how does a mineral reflect light? And in terms of the Earth Science Regents course, materials are either metallic, they look like a metal, or they're classified as non-metallic. So taking a look at our options on the right side, we have quartz, galena, limonite, gypsum, talc, and native copper. So try to take a look at this and figure out which ones of these look like metals. All right, so you can pause the video and do that. Okay, so the very first thing, galena stands out to me. Silvery has this kind of metallic look to it. You just kind of know it when you see it. So galena is metallic, as is native copper. All the rest of the minerals pictured here are non-metallic. Right, so again, the best way to describe this is you know it when you see it. Does it look like a metal or does it not? The next characteristic is hardness, and this is a mineral's resistance to being scratched, measured on what's known as the Mohs hardness scale. It's a measurement of 1 to 10. Right, so down at 1, we have the mineral talc. It's very, very soft. All the way at the top of the scale is diamond. That is the hardest naturally occurring material known to man. So that's diamond. So how does this work? Let's take a look at an example here. We have the mineral apatite right here in the middle. Apatite has a hardness of 5 according to the Mohs scale. Because it has a hardness of 5, it can scratch anything beneath it. So it can scratch fluorite, calcite, gypsum, talc, because all their hardnesses are less than 5. But it cannot scratch orthoclase because orthoclase has a higher hardness. Hardness of 6 cannot be scratched by a mineral of a hardness of 5. All right, so very common Regents type question is figuring out what mineral can scratch another, and any question along those lines will give you some sort of hardness scale to work with. You do not need to memorize any of this information. Breakage is how a mineral tends to break, and that is subdivided into 2 categories, either cleavage or fracture. Cleavage is when a mineral breaks along lines of weaknesses within the atomic structure. Right, so these are inherent weaknesses that are built into the kind of crystal structures of these different minerals. And because they are in the atomic structure, they're going to repeat in sort of a regular pattern. So we very often see repeating parallel surfaces, which often look like they've been cut and can look like they're stair steps. So what do I mean by stair steps? So very often you will see minerals that have this kind of stair step pattern to them as a result of their breaking. Okay, so they can kind of look like the mineral here on the left, where we have one side here parallel to that, parallel here. This looks like a sample of halite. And we can even see in the little notch here, these breaks are still parallel. Right? So it kind of looks like a rectangular piece that's been broken out. This is another example of a type of cleavage where we have muscovite mica breaking into these thin sheets. Right? So think about a sheet of paper. So that sheet of paper has a parallel side. So the top and the bottom are parallel to each other. This is actually known as a book of mica because these are sheets or pages of the book. The other type of breakage is fracture. All right, so when you don't have any sort of inherent weaknesses within the atomic structure, you tend to have minerals that break along sort of these curved or random surfaces, which result in sort of this irregular shape. Very common in the mineral quartz, which is pictured in both of these examples. So we have these curved surfaces, and this almost looks like it's broken glass. So that is what fracture would look like in hand sample, which brings us finally to color. So color you have to be very, very, very careful with in terms of identification or using it for identification purposes because many minerals occur in multiple colors. So we're going to take a quick look at quartz as an example of this. So the mineral quartz is typically colorless, but it could also be kind of this white or sort of translucent milky color that's known as milky quartz. It can be smoky quartz, so kind of a gray to black color. Purple variety is known as amethyst. The yellow quartz is known as citrine. We have rose quartz, and almost any other color under the sun. All right, so this is just one example of why you wouldn't want to just look for sort of the colorless variety to identify quartz, because an amethyst is still quartz. Right? The other thing about color is not only do certain minerals appear in many colors commonly, multiple minerals can be the same color. So there's lots of minerals that are colorless or white in color. So it's not a great way to identify minerals. What's more useful than color is streak. Okay, so streak is the color of a mineral in its powdered form. And you determine the streak by rubbing a sample onto an unglazed porcelain tile, which is known as a streak plate. These are typically white or black, and you just pick up the mineral sample and sort of drag it across the tile, much like you would drag a crayon across a piece of paper. All right, so interestingly enough, sample on the left, sample on the right, they look very, very different in terms of their bulk color. So this is kind of this dull red color. This is a metallic gray or silver color. Both of their streaks are identical. Okay, so the streak is a little bit more useful than just the bulk color alone.